Okay, so today, tomorrow, and probably a little bit of Wednesday, I wanna work on graphing these transformations. Okay, the reason we're going to spend time graphing these is this is the preliminary steps for the first technique for solving trigonometric equations. When we solve a trigonometric equation, if you're uncertain about what to do, you can always result back, or I guess turn back to the technique of graphing the left-hand side of the equation, graphing the right-hand side of the equation, see where they cross. To establish that ability, we need to be able to obviously graph this side of an equation, okay, the trigonometric side, okay? So, what you're going to do, first thing you're going to do is decide what is the trig function, okay? So the trig function here is cosine. There's a couple different techniques you can use. I bounce back and forth between multiple techniques on graphing these, but they both include having the parent function in front of you. Okay, whether you have the parent function on the side in a small sketch, or if you actually put the parent function on your current graph, either one is fine. Okay, so what I'm going to do in this one, let's just go ahead and put it on the side. If there's just a few amount of transformation, only one transformation, maybe two transformations being done here. I'm going to do them in the same step though. Then I think it makes sense to put the graph on the side. Okay. If ever I've got a left and right, up and down transformation, okay, horizontal and vertical shifts, I'll usually put the parent function on the graph. It's just what makes sense for me, and you decide what makes sense for you as well. But I'm going to graph cosine of x. I want to think about that thing first. So I'm going to graph that parent function, which we said on last week starts at 0, 1, finishes at 2 pi 1, at pi negative 1, and then we have our x-intercepts at the pi over 2 in 3 pi over 2 increments. So that's our cosine function, correct? Okay, and this is the importance of being able to graph that thing efficiently and understand these ordered pairs like the back of your hand is because of how that then gets transformed into actually graphing our -3 cosine x. Okay, so when I type this, I probably should have put parentheses around this x. It doesn't matter. Sometimes you see it, sometimes you don't. But for the purposes of our notes right now, and as we move forward, I want to put parentheses there. Okay, and the reason I want to do that is because there's a coefficient for that x. And in this case, it's going to be somewhat trivial. But what is the coefficient for that x right now? It's 1. Okay, if we go back up to how every single trigonometric function is going to be written in terms of cosine, it's going to be written one of those two ways. Okay? And you can see this b value right there, correct? Okay? Or you can see it written out here. And this is the way I'm going to prefer us write it. Okay? If we look at how the period is designed, the period is always 2 pi divided by that b. Okay? So when we come down here, our b value, we need to identify it, but it's just 1. So when I go period is equal to 2 pi over b, it's 2 pi over 1, which is just 2 pi, right? Which seems trivial. But in the next example, you're going to see how that impacts things, okay? So I want us to get in that mode of always doing 2 pi over b, okay? Now what you're going to do is you're going to establish where do you want 2 pi to be on your graph, on your x-axis. So I'll put 2 pi right there. We'll cut that in half. Find pi. It's not half. Let's go. I'll cut that in half. So 0 to pi will be cut in half, and then give me pi over 2. And then, man, I really messed that up, didn't I? No, that's right. Clean it up. Let's make it easier. Go to 2 pi there. So now pi would be here. Pi over 2. Just try to keep things a little bit to scale, or as to scale as possible. Okay, so now my y-axis, that right there. So what is my amplitude? My amplitude is 3. Okay, remember amplitude is the absolute value of that A out in front, so absolute value of -3. And that just tells me that amplitude is the height that my maximum and minimum reaches from the wave axis, which in this case would be the x-axis. Okay. But another way we could think about that, and then a lot of times I don't even worry or think too much about the amplitude, because that is what we refer to as a scalar multiplier, which is our vertical stretch. If you guys remember, like if I had x squared, and then I rewrote it as 3x squared, what does that 3 do to the y values of x squared? Makes them 3 times bigger. Okay, multiplying by 3. So with that 3, when I take x squared out and replace it with cosine, it's the same thing, right? That 3 takes the y values on the cosine and makes them 3 times bigger. So that point right there, 0, 1, is going to go to what? If it was just a 3 out in front. 0, 3. It's going to go right there. But now that 3 right here is negative. And when I multiply the entire function by a negative, what does that do to the y value? It makes it negative. So it went from 0, 1 to 0, 3, but now negative 3. Okay, so 0, negative 3 will be that point there, correct? And to be honest with you, we're basically done, because now we're just going to go apply the symmetry that occurred here to this thing down here. This thing started at 0, 1. We transformed that point to 0, negative 3, right? Well, the cosine function should start and stop at the exact same y value. Does that make sense? Okay. So that point right there corresponds to that one there on the parent function. Stretched by 3, reflected on x-axis. Okay. This point here, which was halfway, was at pi negative 1. And now it's going to go to what? Positive 3. Pi positive 3. X-intercepts have a y value of 0. So when I multiply 0 by negative 3, they stay the same. Connect with a smooth curve. And that there is your cosine, negative 3 cosine of x. Okay. Now, some people prefer to see this in comparison to the parent function. If I were to compare it to the parent function would be that curve right there. Okay, so this is cosine of x, and the red one is negative 3 cosine of x. You can see the 3 produces a vertical stretch. Okay, that value stretched vertically, that value stretched vertically, and then they're reflected, right? Does that make sense? Okay, anybody have questions on that? Vertical stretches, when we don't alter the period, they should be very straightforward. Okay. The questions that get difficult are when we start altering the period, which I wouldn't say they're the hardest. They're a little bit more challenging. The most challenging are ones like this, where we we alter the period, and we move them left and right. Left and right movements are going to be tricky for us, okay? But let's go ahead and work our way slowly through something like that. So here, we'll talk about 4 cosine of 3x. 4 cosine of 3x. Trying to get a decent. There we go. All right, so what I'm going to do here for cosine of 3x, 4 cosine of 3x, I'm going to first graph up here cosine x. Okay, so I want to draw them comparative to one another so you can see what the actual transformations end up doing to the overall graph. So I'm going to make this a height of 1 there, height of -1 there. Let's make this out here. Let's make that 2 pi. That pi, pi over 2, 3 pi over 2. So cosine for 0 to 2 pi would be that curve there. Is everybody okay with that? Okay. Now, when we see, so this right here, that's your b value. Okay. The period for the cosine is always 2 pi divided by b, much like the period for the sine is. Okay, so b is 3. So now the period is going to be 2 pi over 3. Well, 2 pi over 3 would be about right here. Does that make sense? Okay with everybody? So just to keep things to scale, just so you can see the comparison here, I'm going to make 2 pi over 3 right there. Okay? Now you could, because we're establishing the x-axis ourselves, we could really put it anywhere we wanted to, right? So I put 2 pi over 3 and I lined it up with 2 pi on my first graph. My final picture is not going to look much different than what I started with. Does that make sense? Because I've elongated the scale on the x-axis. Okay? So I just want to make a comparison here so you can see what is happening. But in general, if I didn't care to make that comparison, I'd put 2 pi. I'd give myself as much distance as possible to make things clean. Does that make sense? Okay. But I just try to prove a point visually here for you. All right, so we got 2 pi over 3. So thinking about what happens on our cosine function. Doesn't our cosine function, the way we developed it, the parent function, was that we split it in half? There's some symmetry there, correct? So when I split 2 pi over 3, that symmetry should still exist. So I've shortened the period, so I'm pushing the period down from 0 to 2 pi now to 0 to 2 pi over 3, but the symmetry should still be there. So this is going to be pi over 3. Is that okay with everybody? Okay. So I'm going to color code things. That blue region should be the same as the blue region up here, or corresponds to the blue region up here. And this green one corresponds to that green region, or interval. Okay, then we cut the blue one in half, right? On the parent function? So let's cut it in half down here. What's half of pi over 3? Pi over 6. Okay. Now, if you remember, I talked about once you do that, once you find that pi over 6 distance, that's the I called it the index the other day. That's the counting tool to keep going from 0 all the way up to the end of your period. Okay, which was the same thing as taking the period divided by 4. Well, 2 pi over 3 divided by 4 gives me that pi over 6. The reason I'd be interested in that because it's going to help me find easier that value right there. Pi over 6, that would be 2 pi over 6, and then this would be 3 pi over 6, which is going to be pi over 2. Okay. You can also say it's the average between, because it's the midpoint, right? So you take that number plus that number, divide by 2, and it'll give you that location there. But I want to be able to identify that coordinate. I'll make that 1. I'll make that -1. Okay. Now, remember what we're trying to graph here. We're trying to graph y equals 4 cosine of 3x, right? Okay. Scaling our x-axis this way, we've essentially taken care of the 3 right here. Okay, we've done that transformation. This 4 is going to make every y value turn into what? 4 times as big. Okay. So at a y value at 1 on the parent function right there, it's going to go now to a y value of 4, right? Okay. Then over here on the parent function, it stopped at the same y value, right? At the end of its period. So on the transformation, it needs to stop at the same y value on the end of its period. Okay, everybody? Halfway in between, that point right there on the parent function, was at its minimum, right? At -1. So now halfway in between on the new period, it needs to be at its minimum now of -4. Now that point there and that point there, essentially I call those the quarter points, okay? Because that's a quarter of a way through the entire period, right? And that'd be the 3/4 way through the entire period. But those quarter points on the parent function, they are x-intercepts, right? So then when we transform them, when we change the period, quarter marks still need to be x-intercepts. And now we can connect this again with a smooth curve. And we get that as the cosine function. 4 times cosine of 3x. Can you see, and this is why I drew it to scale in comparison to the top one, can you see that that 3 creates a horizontal compression? Okay, when your b value is greater than 1, when it's greater than 1, you're going to have a compression. Okay, now if we were to like replicate this, so right now, in order to go out to 2 pi, okay, I would need 3 of those. See if I can cut and paste this. OneNote has it's very picky on letting me cut and paste a lot of times. That's a little bit better. Nope. Control-C. It won't let me paste. But if I wanted this to go out between 0 and 2 pi, I would need 1 more of those, and then a 3rd one of those. Does that kind of make sense? Okay. And you can see now that there's 3 oscillations going around essentially the unit circle now than what we were seeing here with the 1 oscillation. Yes. Yes. So and that once you have this initial period, then it's just cut and paste. But they will add, and that's all. based off of instructions. So what they'll say is, like in the directions, they'll say sketch. If here, based on what we did, they would say sketch 1 period. And that's what we did. We sketched 1 period. But if they said sketch 4 cosine 3x on the interval from 0 to 2 pi, then I would need to keep graphing until I got out to from 0 to 2 pi. Sometimes they go negative 2 pi to positive 2 pi. It's just you got to pay attention to how they word things. This next one. Okay, so if we had a number that was bigger than 1 right here as the b value, that became a horizontal compression. This is a number less than 1, right? Between 0 and 1. What's that going to do? It's going to stretch it. Okay. So let's see if we can produce that function. It is the sine function this time, so be aware of that. This thing's frustrating. Control C, E. All right, so if I graph y equals sine of x, and just because I know there's going to be a vertical stretch here, a horizontal stretch, I'm actually going to make this parent function just so you can see the imagery here. I'm going to condense it a little bit. Let's go 1, negative 1. So the sine function I totally messed that up. Sine function is going to look like that. Okay. So now, if we're going to go negative 2 sine of 1/2 x, first thing you have to do is identify the period. Period is equal to 2 pi over b. What is the b value here? 1/2. So 2 pi divided by 1/2 ends up being 4 pi. Does that make sense? Okay, so I'm going to make this out here 4 pi. Cut this in half. I get 2 pi. Always going to be doing that, cutting in halves and then cutting in fourths, just to get that symmetry. The symmetry, there is nothing we'll ever do to these functions that the symmetry disappears. Okay. So then, we've basically, by developing this x-axis, we've dealt with the 1/2 of x so far. Now the negative 2. What's the negative 2? So on my parent function, I have this point pi over 2, comma 1. What's that negative 2 going to do to that 1? It's going to make it negative 2. Okay, so on the parent function, that happened halfway in between that first interval, right? Which was 0 to pi. But now when we stretch this out horizontally, it's going to happen halfway in between that interval from 0 to 2 pi. Okay, so this will end up being pi, and this will end up being negative 2. So pi, negative 2. Is that okay with everybody? Now halfway in on the green interval, we were at a height of negative 1, right? So now halfway on this green interval, we should be at a height of positive 2. Okay, so this point here at 3 pi over 2, comma, negative 1, that negative 1 gets multiplied by that negative 2, turns into positive 2. Okay, what happens with these x-intercepts? What happens to those y values? They stay the same. They stay 0. So this one was 0. Okay, now this one does get stretched out to 2 pi. and the 2 pi one gets stretched out to 4 pi. But now, okay, that should be negative 2 sine of 1/2 x. And you see the horizontal stretch, you see the vertical stretch, and the reflection. Is that right? I told you there's several different techniques that can be used. Some people, and I'm actually going to do this on the next one, but some people will take and graph them kind of simultaneously on the same graph. Okay, so we'll start with sine of x. Okay, then they'll say, okay, well, I know that sine of 1/2 x is going to stretch it like that. And they say, okay, well, then once I take those, if I take, let's just find these critical points here real quick. So what it's going to do is to say, okay, well, now that I've stretched it out to 4 pi, okay, we can now take this point here and reflect it across the x-axis and stretch it by a factor of 2, and then do the same thing with this point of f, and what we'll end up with is then negative 2 sine of 0.5x, and you can see that this point here would be that one there. Does that kind of make sense? So they graph like each transformation in order all together at once. And it gets kind of messy, right? But you can then get an appreciation for what do we start with? Started with that one. And then when we compare it to the one that we finalized with, this gray one, you can see they're in tandem now. You can see that if I stretch this one horizontally and stretch it vertically, and then reflect it, it will end up being this gray one. Does that make sense? All right, so this one here, and I'm actually going to write this one a little bit different. I've got it written right now in the format that we want to get it to. But let's just go ahead and ignore that. And let's just write y equals, so this is what we're going to graph. Y equals, did I have it as 3? Okay, 3 sine and we're going to go 2x minus pi over 2. Okay? Now, as we work through this, we should develop a procedure that we can follow regardless of what the 3 is, regardless of what the 2 is, regardless of what the pi over 2 is. Okay? So once we can do this a couple times, procedurally, we can insert any values that we want to in there. Okay? So, right now, that pi over 2 is different than anything we've seen so far, right? We haven't had any that had that subtraction in the argument. Okay? Does anybody remember what that subtraction in the argument is going to do? Okay, it's going to, in this case, because it's minus, it's going to move it to the right. What would your guess be at what the distance that it's going to move is? Most people are going to guess that's pi over 2. Okay? But that is actually incorrect. Okay? Because there's a factor of 2 here. Okay? It is only a phase shift. Pi. Remember what we did when we did phase shifts? Like when we did, like if I had like x squared and I did it this way, as x, like that was a phase shift to the right 3 units, right? But what is the x? What's the coefficient of the x right now? It's just 1, right? So that was a direct shifting 3 units to the right. Okay. If I would have written it as like 2x minus 3 squared like that, let's kind of look at that real quick and see. So if I would have started with like x squared and then went 2x minus 3 squared, did it shift all the way to to the right 3 units. It went 1.5. It went half of that, didn't it? Okay, so that's kind of the same thing. We didn't see too many of those because if you remember back when we talked about polynomial functions, we didn't deal a whole lot with the horizontal compressions and stretches because they look very vertical in their stretch. So we try to avoid it. And doing that, it didn't allow us to maybe see that very often, but we are only going to be able to identify algebraically, or maybe even visually, I don't even know if algebraically is the right word, visually, what our horizontal shift is, or what they call a phase shift, when the coefficient for your x is a 1. So what you're going to do is you're going to factor that out. You know, y equals 3 sine, put a 2 here. I'm going to fix this in a moment, but I'm going to put a 2 right now. And then I'll write my argument. This 2 is still part of my argument, though. We just got to make sure that we understand. That's what I mean. I'll fix it here in a moment. But what's 2x divided by 2? X. What's pi over 2 divided by 2? Pi over 4. And the way that I always do that, guys, because it gets confusing, especially when maybe I got to factor out like a 1/2 or factor out a third or something like that. Instead of dividing pi over 2 by 2, isn't multiplying by its reciprocal the same thing as dividing? So I multiply pi over 2 by 1/2. That's still divided by 2, which gives me pi over 4. Now I'm going to do this. This is what I was talking about when I said I was going to fix it. Because that 2 still needs to be part of my argument. It's still part of, you know, the sine, this input here is an angle, right? Okay, so that 2 is still a component to that. But now we can see that is your B value. And this here is going to produce your phase shift. Usually I abbreviate that PS. Okay, so period 2 pi over B, right? So period is just pi. Phase shift, pi over 4, which direction? Right. Which again, if we compare it to the original way that the problem was written, that pi over 4 is not explicit. Okay, it's not easily identified. So now we're going to construct our axes. When there's a phase shift, what I like to do is I do a combination of looking at my parent function and a combination of graphing on top of the current graph, okay? So we know it's a sine function, so my parent function is going to be that, okay? But now down here, bless you, my period goes from 0 to pi. So just like the parent function, we're going to start cutting that in half. Pi over 2, pi over 4, and then 3 pi over 4. Okay. Now, I just know because I've done enough of these, okay, that I'm going to, everything's going to be moved to the right pi over 4 units, right? So normally this thing's going to stop at pi. But because it's going to be moved to the right pi over 4 units, it's actually going to stop at 5 pi over 4. So I'm going to add one more interval here, okay? You could do that at the end, or you can do it now, like foreshadowing, knowing that that's going to occur. All right, so if I just look at, so right now what we've done is we've kind of dealt with the 2x by writing our axes this way. Okay, that was the period. We've got the sine function here. What's this 3 going to do to my sine function? Multiply every y value by 3. So initially, before I do any phase shift, so what I'm going to graph right now is 3 sine of 2x. 3 sine of 2x, because that is everything that I want except for the phase shift, right? Okay, so I'm going to graph that. So the 2x has already been done because I've got the x-axis the way I wanted it. Okay, so basically that means that that point, and that point are good to go. Okay, those are the points up here on the parent function that were x-intercepts, right? This point here that was halfway in between the first 2 x-intercepts was at a height of 1, but now it should be at a height of 3, right? And then this one here, halfway in between these 2 x-intercepts, should be a height of -3. Okay, so I plot that. Those points would be 3 sine of 2x. Now every one of those is going to get moved where? Pi over 4 to the right. And now it's, because of the way we set up our x-axis, it's just one interval, right? It's one tick mark moved to the right. And that's something to pay attention to. I didn't mention it when we were graphing this, or setting up the x-axis. We want our x-axis to be written in terms of our phase shift, just to make things easier for us when we get to this point of moving points, okay? If my x-axis was in terms of force and my phase shift was in 6s, that'd be very hard to make comparisons, right? Okay, this one was, by coincidence, this pi over 4 phase shift and the way the x-axis worked its way out were the same. If they were not the same, we would have to go through some work to make this x-axis in terms of 6s or whatever. And in this case, so if this was, if my phase shift was in like 6s, but this was in force, I would probably try to make the x-axis in terms of 12ths, because then I could shift in terms of 6s. Does that make sense? And that's a byproduct of this course, is being able to work with your fractions in that kind of manner efficiently. So this point, and this is what I was talking about last week, where if I use points or dots, then maybe when I shift this one to the right, maybe I use like a triangle. And then I shift this one to the right, shift this one to the right, shift this one to the right, shift that one to the right. Does that kind of make sense? And now I can connect the smooth curve with the triangles, okay? But if I just put a bunch of dots, would it be really hard to decipher which dots need to be connected when I'm done? Does that make sense? Okay. Or if you want to put asterisks or squares or whatever you want to use for your symbol here. Now I'll connect those. And we've got our curve, okay? Now, right now, our curve is between, on the interval of pi over 4 to 5 pi over 4. A lot of times, they're going to want it from, at least to start at 0. So if I started at 0, so this is all symmetric, right? Okay, so right here, this portion that is right here would be symmetric to the portion that is right here that is missing, right? So I can fill that in if I want. And now I'm going to go through here because I think we got, what we get out here, 50. All right. I'm going to put these points. So this would be 0, -3, pi over 4, 0, pi over 2, 3, 3 pi over 4, 0, pi, -3, 5 pi over 4, 0. I'm going to see if I can type those in to GeoGebra here. 0, -3, pi over 4, 0, pi over 2, 3, 3 pi over 4, 0, pi, -3, and 5 pi over 4, 0. Plot those points, and let's see if they do then end up on 3. Was it sine? 3 sine of 2x minus pi over 2. Do those points show up on there? Yeah. Okay. My hope is that what we understood about transformations in college algebra, if we understand what transformations impact the x values of the parent function and what transformations impact the y values of the parent function, if we apply those to the x and y values of the parent function on sine and cosine, it produces transformations just like we did in college algebra. Does that make sense? Okay. We haven't seen any here with vertical movements, okay? But remember, if there is a vertical movement, you want to do that dead last, okay? Because that will then save you from having issues with a reflection across the x-axis if one is present. We're going to spend a little bit of time doing this again tomorrow. Obviously, this one's even more complex here. The one thing to kind of think about on like a test or a quiz, I can't ask you to do like 5 or 6 of these, right? Okay, so keep that in mind. But tomorrow we will have a short quiz over the graphing we've done so far.